Yeah, my name is Pradosh. I'm going to talk a bit about the origin validation framework that we have been working at the IETF CIDR group. There are many folks from the CIDR group who are present here, so we can have more discussion on the things that I don't know about. So motivation, I think the talks before me, especially Sharon's talk and the following talk as well, gave quite a bit of introduction into the problem definition. So I'm not going to spend a lot of time on that. But in a sense, the motivation for the work, at least the origin validation work, has been that any AS can inject any prefix in BGP today, and that we would like to call as prefix hijacking. It's mostly mistakes, it's mostly configuration errors, and the aim, in essence, is to provide a solution to that factor, but it could be malicious, as Sharon's talk mostly focused on. And the manifestations of that would be, someone else announcing someone else's prefix, or someone else announcing a more specific someone else's prefix. This is an example that I borrowed from one of the slides, which shows how, if someone else announces a prefix, the shorter AS path wins, and that's how you're able to, attract the traffic. Here it shows a more specific route from the actual victim, and the way to attract the traffic for that. And the famous YouTube hijacking example that basically shows an example of more specific hijacking. So this is where the RPKI, I'm not sure how many of you are totally familiar with the RPKI framework, but in essence, I would just like to view the RPKI or define the RPKI as a framework to create a trusted data store, and everything else that entails to create that trusted data store, and how the end users can benefit out of it. So the main components, to me at least, the main components look like the following 4 or 5. One is the object format, which is where we reuse most part of the certificates, the entire PKI framework as we know of it, with the already defined extensions for the resources that we are interested in, which is basically the IP addresses and the AS numbers, and a way to bind that. And the way to bind that is what we are interested in, because that gives us the trusted, sort of the trusted notion that this IP address or this IP prefix, when it is announced from an AS, it's a valid or authenticated one. And that's the one that the second part provides, which is ROA, or route origin attestation, and we'll go to an example of how that looks like. Then there is the active side of the RPK as well, which is the allocation hierarchy. How does, it all starts from the allocation policy is one today, the routing policy is one today. From the allocation policy, how does it flow all the way from the root, the INR, to the RIRs, to the LIRs, to the ISPs? And how does the trusted data store that the RPKI aims to provide, how does that create it through this hierarchical process? The same with the database maintenance. How does the database get maintained, and how do we get the data out of the database to verify what we want to verify? The transaction semantics. If one owner of an IP address wants to suballocate, an address block, how does that transaction take place in a sort of a secure manner, as well as certificate checks, the CRLs, the revocations, and all that. So that's the active side of it. Then the part that I was mostly interested in focusing on is getting the data to the BGP speaking routers, and what does it mean to a BGP speaking router, and what changes are really needed, or that we want to do the origin validation. So ultimately, when a neighbor or when a peer sends us the route, an update message, how do we know that that's a valid one, or if it is invalid, how do we discard those? So yeah, I was mostly going to focus on that, but then I borrowed some slides from Randy to talk a bit about the overall big picture of how the RPKI data store looks like. So I'm just going to project it here and try to explain it. If not, I'll ask Randy to explain more. So one of the complete pictures from from how the RPKI would look like. The top portion is what how the allocation should look like. You have an IP address block, so you need to get a certificate, proving the ownership that you are the owner of that IP address block, similar to an AS number. That's a resource, and we need to be totally verifiable that you are the owner of that AS number. So the top portion talks about how an RIR or LIR or an ISP would look like. Typically, there would be a back-end process which is with the front end providing the GUI to configure the address allocations and stuff. So that's what one part of the RPKI process fits in, which is called as an RPKI engine to issue certificates, to issue ROAs, and to publish that to the RPKI store or the trusted RPKI store. So once we have those objects published, that's where there's the middle database that shows that this is the resource PKI framework. Once that's essentially a distributed framework. There is a root and there is a hierarchy, and the database exists which contains all the certificates and the signed objects. Then there is a protocol that periodically fetches the data from that RPKI store, and then there are certain more objects that are created called cache or servers. So in a later slide, we're going to show how the servers are placed, or where the servers are placed, and what do they do. But those cache are essentially getting a cache off the RPKI store locally, so that rest of the routers and other hardware they can use the resources. Once it comes to the cache, then there is a separate protocol that is defined, that we have defined. It's called RPKI to router protocol, that takes the data from the cache and has a secure session to the actual end BGP router, BGP speaker, to get the data in a binary format. Once you get the data, you build the database locally on the speaker, and then you validate the route announcements that we receive. So again, this is again showing how do the cache hierarchy could look like if it's an extremely large ISP. The solution to all of the world's scale problems is by creating hierarchies. So you can create hierarchies where you can have caches in Asia, in North America, and Europe, and then the next level of hierarchy of caches, or each POP can store a cache or two for redundancy purposes, and then it can go down there, or ultimately your BGP speakers or BGP routers at the edges can connect to one or two of these caches to receive the RPKI data. So one closer look at the ROA, like we talked about, ROA is a signed object, and it binds an IP address block to an AS number to say that this AS number is authenticated to or is authorized to announce this IP address block. So it indicates the address prefix or explicit authorization that an AS can rightfully originate a prefix. And the format of that from the BGP, from somebody interested in BGP, looks like the AS number and the prefix block, the prefix / mask, and the max mask length. So ROA, and this is an example of that. So once we have the RPKI side of the repository sorted out, this is again a closer look at how the BGP BGP side of the implementation looks like. On the extreme left, it is the distributed RPKI repository. From the repository, like we talked about, there is a protocol which would like to call the arsenic. There is a protocol that the cache uses to fetch or gather the data from the distributed database. And then we assume that there are one or two of these caches either in POP or somewhere local to the router that the router can connect to get the data. So that's the next part, which is the cache to router protocol. It's nothing but a simple SSH session with a format defined to fetch the IP address to AS number or IP address block, IP prefix to AS number mappings. Once the router gets that data, it creates a validation database, which is essentially a tree of storing the IP address blocks to these AS number mappings. So that's one part of the implementation. The other part of the implementation is when the router receives prefixes or updates from the peers, it then goes and looks at this prefix validation database to figure out whether the AS number that the update came out with, the origin AS number as claimed from the update message, is actually a valid one. And based on that, it takes some action, and the action will be described in a later stage. The details of the cache to router protocol, like we talked about, it's a secure SSH session between the router and the cache, and it is a serial number based binary exchange of PDUs containing the prefix to origin AS mappings. On the right side, a typical sequence diagram of how the exchanges would look like. When the router comes up, it basically creates a SSH session with the cache or with one or more caches that have been configured. And it sends something called a reset query PDU that basically says, give me a dump of everything that you know of. And that's when the cache sends back, again in a format which is defined in terms of TLVs, to send the data like IPv4 prefixes or IPv6 prefixes, all those in separate PDUs, and each of them is associated with the serial number back to the router. And when it is done with the data, it just sends an end of data. So that's for the initial dump. After that, the protocol defines a format by which the router can periodically go and query, if you have new data, give me. Or, like the normal notification mechanism that we know of, the cache can send asynchronously a notify PDU with the latest serial number back to the router if it has new data, and then router goes and fetches the new data. So on the router, once we have the data built, or the database, the prefix validation database, which forms a tree, which is the mask and the prefix mask and the AS number. This kind of gives a pseudocode or algorithm of how the validation logic would look like. So one essential part of this is because the ROA contains prefix / mask length and a max length as well. So this is the AS is allowed to originate prefixes that belong in this particular range, which is the mask length that is provided and the max length that is provided, the maximum length that is provided. And the algorithm essentially takes that data, and when it validates, it creates 3 states for the data, for the update message that it receives from the peer. The states could be valid, not found, or invalid. So the valid actually means that I received a prefix announcement or an update message from a peer, and the origin AS that I derive from that update message is actually the origin AS that matches against the validation database. Then, of course, the announcement is valid, and I can accept it, and then process it as well as send it to all my peers. The other state could be invalid, which essentially means that the prefix actually exists in the database. So there is a prefix with the mask length that matches the database. But the AS number that the database tells me does not match the AS number that the update message came with, or origin AS number that the update message came with. In that case, it is invalid, and I can take some actions based on it. And the third state, of course, is not found, because we cannot always assume that the database is complete, especially through the gradual migration process that we would be deploying the new RPKI framework with, in which case the prefix does not exist at all, and the result, of course, would be not found. So this gives the algorithm for how do we derive those states. So once we derive the states, what actions can the router take, or what actions can the BGP speaker take? And this slide talks a bit about, a second in the life of an eBGP update, kind of. So the eBGP update arrives on the speaker. We gather the origin AS and validate it against the validation database like we talked about. So that's the first step, check and mark the origin validating. After that, the implementation allows for matching against the states that we talked about, which is valid, invalid, or not found, in the usual inbound route policy that you apply to the neighbor. So you can match against the state of being invalid and drop all the updates, for example. So that's the next step, that apply the inbound policy, and the policy may match on this validity state and set arbitrary attributes. So once the once the inbound policy evaluation takes place, you add that to your edge ribbon and process and run your decision process, and the next steps go on. And then you take those prefixes and send it out to your IBGP peers or other eBGP peers. So some examples of the policy that you can apply on the inbound side of the neighbor. The typical match statement: if the origin validation state is valid, then apply a higher local pref than the usual local pref. You can set it as 50 for the ones that are not valid, and set 100 for the ones that are valid. That's a typical way of saying that I always prefer the ones that are valid prefixes according to the validation database, and not prefer the others. Another example could be you set the med, not the local pref, because that's the highest in the decision process, but set different types of meds based on whether they're valid, not found, or invalid. You could also choose to drop all the invalid routes by just matching on the invalid state. So the decision process changes from these states. Again, this is optional, because by default, what would happen is you just mark them based on what you have searched for, what you have looked for in the validation state. Then you apply, then everything else is left to the operator, that you apply your usual policy and set the existing attributes to prefer one versus the other. There is also another process that is defined that we have worked on, which is enabled by configuration only, and it automatically matches on the states that the validation process came out with. So as we talked about valid, not found, and invalid, you just assign different states, and you just insert a step in your decision process that prefers valid to not found to invalid, and this is defined to be before the local pref comparison step. And of course, the implementation can do different types of policy overrides. You enable, disable the prefix validation marking globally or on a per ABGP peer for a particular set of prefixes that if you're interested in. Then similarly, the enable, disable, validate state comparison in the decision process, the same kind of knobs globally per ABGP peer and for set of prefixes. And then what are the default values and how do you change the default values? Another interesting part of this is because the prefix validation happens only on the eBGP side that you receive from your eBGP peer, either from your customer or from your peer, and you would like to validate the prefixes, and set a particular marking. But how about when you send them to your iBGP peers? How do you convey the fact? How do you automatically convey the fact that this particular state is valid, or this particular state, this particular prefix, the state is invalid or not found? And that we have defined an extended community to just propagate that state back to your iBGP peers, because they can also do the similar comparison that you did. So a bit about status. For all that we discussed from BGP perspective, the prototype code on for the part that is on the routers is available both on iOS and XR. And Ed is sitting right there. You can contact if you're interested to play around with it, experiment with it. Similarly, for the RPKI implementation that we saw, the RPKI engine and creating those certificates and stuff like that and publishing, that is available as open source. And here is the pointer to the open source. If you'd like to, get that into a cache or whatever. And this is just showing a picture of the open test bed that people have been playing around with, and who have RPKI engines already implemented, already there to issue the certificates and store the certificates. And this is where the RPKI trust store or repository would look like. About the configuration commands, so just a detail into the configuration commands of how you would, if you would like to play with the router. You would configure a cache with the cache name and port number. So right now the prototype code just has a TCP connection to the cache instead of an SSH. So this is a configuration for just configuring a TCP session with the cache to get the data. And then the usual knobs of either validating, enabling the validation so that you start marking your BGP updates, or you can have a knob to compare the validation state to automatically in your decision process with knobs whether to allow the invalid or not allow the invalid and stuff like that. And typically the show command, I don't know if you can see the screen, but the prefix validation database that the speaker has built, just a show of that. And similarly for the marking, once the marking is done for the prefix, you can again see it with the usual show BGP command with the origin validity state at the last side. That is the extra which says whether it's valid, invalid, or not found. Here are some of the references, and of course the CIDR working group has all the drafts there. Questions?
Questions?
I know folks are hungry.
Okay, thank you very much.